Thank you very much, Professor Bono, Dr. Miller, ladies and gentlemen. We have just had a review of the indications for left ventricular assist devices, and yet you have heard bridge to recovery was very, very small proportion of the total. In contrast, I believe that the most exciting area in left ventricular assist devices support is the bridge to recovery, because I submit to you that it actually, apart from many advantages which I can talk about in a minute, but I'm not going to really be comprehensive, the fact that there are adverse events associated with the use of long-term continuous flow pumps, and getting rid of the pump and having a normally functioning heart for periods of up to 10 years is one of the most exciting things we have seen in cardiology and cardiac surgery, because it also holds the secret of finding the molecular causes of heart failure and identifying new targets. So in this talk, which I have to be brief, really I start by talking about the enigma of heart failure, because up till now we don't know the basic mechanisms of heart failure, and it's all approximation, and I will talk about pathogenesis. Most importantly, I will be concentrating on the potential for recovery, and importantly on the putative mechanisms of reverse remodeling or recovery and what that means. And then I'll end up my talk about strategies to enhance recovery from the picture, dismal picture Dr. Miller has shown you, and talk about what's next. Now, I'll be very quick because there are many experts in the audience, obviously. We all know the global epidemic of massive proportions of heart failure, and we've had from Dr. Bono a masterly review of the situation, the poor prognosis, the burden, etc., etc. You have had all that. And as again Dr. Bono and Dr. Miller have indicated, the treatment using drugs have been palliative, because there is no specific cure. And there are some exciting movements in the paradigm trial recently, but again, it is not tackling the basic mechanism. And therefore, we really have to, if we are to cure this condition, understand what are the basic mechanisms. And in heart failure, you have cardiac changes, and they are both structural and functioning. And for the lack of a better term, we call it remodeling, because adverse remodeling, to differentiate it from any other type of remodeling. There are vascular coupling, as we have learned, and because it's a cardiovascular change. And importantly, there are neurohumoral changes which could contribute to the pathogenesis of heart failure. And indeed, that has been the target for medical therapy up till recently. Now, what is the potential for myocardial recovery? Well, up to recently, conventional wisdom had it that adverse remodeling is relentless, with minor temporary remissions. Now, new recent trials showed evidence of minor reverse remodeling. You have heard that apart from some medical therapy like beta blockers and with Mike Bristow, but we heard from Dr. Nidal just a few minutes ago that device therapy and biventricular pacing can produce a degree a degree of reverse remodeling, but not substantial. The only method which has, I submit to you, which can produce considerable reverse remodeling is the so-called bridge to recovery. The only problem is that it is only in some patients. This indeed offers unprecedented opportunities, apart from benefit to the patient, to unravel the secrets of heart failure at cellular and molecular levels. Well, let us look at, I'm now concentrating on reversal of adverse remodeling and who are the major players, and I will show you the evidence so far. Because before we can modulate that, we really have to define it. And the major players are, as you would expect, first the myocyte, and I will show you some of the changes. I cannot be comprehensive at this stage. Microvasculature is very exciting area. Fibroblasts not only affect the physical properties of the myocardium, but you have heard from Dr. Despina Sanudo that actually the fibroblasts talk to the cardiomyocytes and influence cardiac function dramatically. And indeed, clenbuterol, which acts on cardiomyocytes, acts through the fibroblasts, and you have shown in your talk, Despina, how certain mirs can affect cardiomyocyte and influence myocardial function through the fibroblasts. And that's very exciting indeed, because I think fibroblasts has been the neglected Cinderella of heart failure. And we and others are really very, very interested in fibroblasts. I won't talk to you more about that because I haven't got time, but this is a very exciting area. The matrix, and you will hear tomorrow in tissue engineering from one of our scientists. Is he here? I can't see. Oh yeah, he's there. About how important the matrix is, the three-dimensional architecture, the chemical composition, mechanoreceptors, the crosstalk, the niche, etc., etc. I'm not going to steal his thunder. He will tell you all about that tomorrow. So I will just limit myself to the myocardium and the microvasculature. Just simple. What about the myocardium? I'm not going to be, again, tell you everything, but I will concentrate on obvious things. And that is, the first thing we see in reverse remodeling is the change in the size and shape of the cardiomyocytes. And that could have an influence on slippage, but much more importantly, we know that the cytoskeletal proteins actually act as transduction pathways, and this is really important. I will tell you more about cytoskeletal proteins, whether they are sarcomeric or non-sarcomeric. They really do play a major role, and I will see in reverse remodeling. Again, it is association studies. I will show you more. Then comes calcium handling protein, and we have heard repeatedly, I think, from more than one of the speakers about the role of the central role of calcium handling proteins. I will not go on about beta-1 and beta-2 receptors, G proteins. Cytokine expression does play a major role. At one time, it was thought that the so-called inflammatory response is coming from the gut, and that was the theory in vogue at one time. until it was firmly recognized that actually the pro-inflammatory cytokines are actually induced in the heart. And you don't need the gut to produce IL-1, IL-6, TLR4, etc. And so in reverse remodeling, we see that this inflammatory response in the heart is actually reversed. So I'll just show you some of our own experience. You see here, this is the Hairfield program, which has been published in New England Journal of Medicine of a combination therapy. And we have observed about 60% of non-ischemic cardiomyopathy. Actually, we could take the device out. This could not be repeated in the US with a multi-center trial in which Dr. Miller was part of it, and for a variety of reasons, not least that we couldn't get clenbuterol in the States, and also the frequent people adhering to the protocol, etc. But please note in the central panel, these are the cardiomyocytes before or at the time of insertion of the device from the disc we take out from the apex. They're huge, and their shape is different. But this work was done by Chester Acciano in our group, and he shows that the cardiomyocytes revert to the normal size and shape, very comparable to normal cardiomyocytes which we obtained from donor heart at the time of transplantation. Normal cardiomyocyte, that's the best we can do. We can't take biopsies from people walking in the street. But the next thing, Chester Acciano in our group had a seminal paper where we showed that this diminution in size and shape does not translate into recovery. And at that time, we showed that it was actually changes in SERCA2 and the calcium content inside the sarcoplasmic reticulum, which correlated with recovery. So this was like a surrogate marker, but not 100% of recovery. Then came the role of looking at changes in both sarcomeric, but also importantly, a lot more in non-sarcomeric proteins. And this study was published some time ago from our group, looking at non-sarcomeric cytoskeletal proteins at mRNA level. This was later confirmed by Najma Latif, both at protein level, looking at both sarcomeric, but also a non-sarcomeric, which was the prevailing thing, but also at sarcomeric. And there were these changes observed in mRNA were confirmed at protein level. Then comes the massive work on changes in the proteins involved in EC coupling, calcium handling, because that is the secret of the myocardium. Don't worry, I'm not going to go through all these. These are different papers and the different changes. And the most important, to my way of thinking, is the calcium content of the sarcoplasm and the changes in SERCA2. There are changes in the ryanodine receptor. Later on, our group and others, we've been concentrating on changes in the T-tubule, because importantly, the T-tubule contain a lot of the receptors, and there is change both in the shape and function of the T-tubule with recovery. But these are just a summary of the changes which occur with reverse remodeling at myocardial level. Now this is quite exciting. I showed that slide once because this is the same patient at the time of implantation of the device, showing this huge cardiomyocytes. And that's the same patient I took a biopsy at the time of explantation of the device when he has recovered. And interestingly, you can see all these, the massive change in the size and shape of the cardiomyocyte. I showed that slide in one of the meetings, and Piero Anversa jumped at me and said, of course, why do you say they are the same cardiomyocytes? These are new stem cells which has repopulated the cardiomyocytes, and I can prove that to you. Well, we have never proved that, because I still think that probably it is the same cardiomyocyte, but there is now emerging evidence that indeed either cardiac-derived progenitor cells, I shouldn't say stem cell, but also dividing cardiomyocyte is an exciting area, extremely exciting area, and we should be concentrating on that. This is a very interesting work by Stavros Drakos, who used to be in Athens, and he's now in Utah. And Stavros showed very definitively, beautifully, the increase in the number of microvessels with recovery. So this reverse remodeling does not only involve the cardiomyocytes, but also the microvasculature. He did that elegantly using a variety of techniques, but here it's immunocytochemistry using CD34 to label endothelial cells, and quantified it beautifully using digital microscopy, because then he couldn't argue that he's taking only a small part of the myocardium. He could go from epicardium to endocardium and show that there is, with recovery, there is 33% increase in the number of microvessels. He went on, Stavros, to delineate the changes in the size of the microvessels, but also the activation of the endothelium. A very elegant study indeed. Now, I talked about the role of fibroblasts. I will not talk about that, and I talked quickly about some of the studies, again, performed at Hayfield, which showed that with recovery, actually this was severe heart failure, showing with severe heart failure, there is marked increase in TLR4, but also on other cytokines, pro-inflammatory, like IL-1 and 6, and a decrease, I should say, in anti-inflammatory, like IL-10 and IL-14. And this is just showing these are LVAD candidates, it should say, not LVAD, because that's a normal stable heart failure biopsies, and this is patients undergoing LVAD, and you can see increase in IL-1. Now that we know there are so many changes, what are the strategies? Because it is obvious that unloading alone can produce a degree of recovery, but as you've seen from Dr. Miller's slide, it is not enough. So we do need what I call combination therapy. At Hayfield, we use a strategy of inducing maximal reverse remodeling by a combination of pharmacologic therapies, which consisted of beta blockers, AT1 receptor antagonists, and anti-fibrotic agents. And then when the heart got small, we induced what we called physiologic hypertrophy using the beta-2 agonist, clenbuterol. Clenbuterol is a very difficult drug. Why is it difficult? Because although it has been licensed to be used in asthma, we need much bigger doses systemically. And it has earned itself a very bad name because of its misuse in athletes. And all these muscles you see, many of them were, and so everybody was frightened, including the German company producing the drug. They just stopped producing it. And now you can only buy it on the internet from unreputable sources, and that's not good enough. So clenbuterol, we used it because we could get it directly from the company. We begged them, and they produced it especially for us. Dr. Miller didn't they? And then more recently, we've been using ivabradine, and you will be familiar with ivabradine, the funny current inhibitor. To everybody's surprise, including ours, what was said about ivabradine, that it is only specific to the SA node and reduces heart rate. That's not the case. It actually, if you fix the heart rate in an animal model, and that we published on that repeatedly, again, Chester Achano, a group in our lab, if you fix the heart rate, and it does have a reverse remodeling effect, and that can be quantified. So in patients, both in patients and sinus rhythm, because ivabradine, the receptors are not only present at the SO node, but other cells as well, including fibroblasts. Now, gene therapy is a very exciting area, and I was going to talk about it until I heard that Dr. Miller is going to talk about it tomorrow. So I'm not going to talk about gene therapy, because there are many exciting possibilities there in circa-2, but many other molecules which are coming in, and most importantly, the vectors have evolved, and we had about the AAV9, which targets the heart, and we are really sorry that Dr. Roger Hajar isn't here, but we have another great expert in the form of Dr. Miller, who is going to tell us about that, and therefore I'm not going to talk about that. Cell therapy, you will hear a lot about from our lab tomorrow, because I already said that bone marrow-derived cells have been a great disappointment. The so-called cardiac progenitor cells with the Scipio trial and the other ones too, we feel that they are also disappointing, and that the future is only going to be in actually repopulating the myocardium with new cardiomyocytes. Well, there are very exciting possibilities there. One is the pluripotent cells, and you will hear about that from my colleagues tomorrow, working on IPS and also in ES, embryonic stem cells, but they will also talk about nuclear transfer just for completeness. Nuclear transfer actually might come back. Dolly is cheap. There could be future there. I think one of the most exciting, and I'm going to end my talk about, is the work of Hisham Sadeh, where he shows he has been working on enhancing cell division, and he has published several papers on the mechanism of myocardial cell division, which without doubt occurs in many animal models, and I will show you more. It happens, for example, in the zebrafish. It happens in the salamander. You cut half of the heart of the salamander, it regenerates completely. Now, Hisham also has been looking at something extremely interesting, and this work published recently, very recently in Cell, shows that during embryonic life, the myocardial cells are dividing rapidly, and they continue to do so for a week after birth. But he showed that, similar to the zebrafish, there are two things. He has developed that further, is that there is low oxygen and there is low pressure. Now we have heard the elegant talk of Dr. Shana Yacoub about the problem of ROS, reactive oxygen species. Now, Hisham showed that reactive oxygen species, following birth, there is massive increase in the number of mitochondria, and he theorizes that's because the heart has to cope with the massive increase in load. It wasn't pumping, and it was hypoxic, and it was at a low pressure. And with the increase in the number of mitochondria, he shows definitively, I might say, increase in the active oxygen species and damage to the mitochondria, to the DNA, and that stops the cells dividing. And he reversed that in the animal model, obviously, and behold, he shows evidence of the myocytes starting to divide again. Now, I might not be allowed to tell you this, that he has repeated the same work in patients with left ventricular assist devices, and he has shown that the same happens, that there is a decrease in the active oxygen species, and that he showed evidence of the cardiomyocytes starting to divide. This paper is under review with Nature, and I hope it will be published, because it's really exciting. Just because there are issues, this is from the Cell paper, where he shows that the reactive oxygen species can actually damage the DNA, and that stops the cell dividing, and he shows the cells stopping to divide, and when he counteracts that, the cells start dividing again. So, in conclusion, I've shown you a whole lot of things which could be a cause and effect, or it could be associated, and we really need system biology and to have analysis of the so-called complex networks. And there are many people now, this branch is coming up, and if you are faced with a swarm of insects coming, you don't attack them with a broom like this child is trying to do. You need system biology. You need complex networks analysis. And hopefully that will be the way forward. We have already some therapeutic targets, but maybe we will have a lot more thanks to the Bridge to Recovery programs which are developing. And that's why the title is Bridge to Recovery on the Move. I hope on the move forward. Thank you.